Order, order. The Science, Innovation and Technology Committee is in session, and today we have a one-off inquiry into the UK's relationship with CERN, the European Centre for Nuclear Research, to which the committee made a visit earlier in this year, which was very instructive, and several members have been on previous occasions as well. CERN was founded in 1954, so this is the 70th anniversary year of CERN. It has 23 member states, including the UK, and 10 associate member states. It's perhaps most famously associated with the Large Hadron Collider, which we'll be talking a bit about later on. But there are questions about future investment into successors or additions to the Large Hadron Collider, which we will touch on. There can be a lot of quite technical and scientifically advanced concepts here. As you know, the committee stands in the place of all 650 members of Parliament and indeed the public. So please don't assume the advanced scientific knowledge that you might have with your colleagues back at CERN, but help us understand and help the public watching understand the big issues that we have at stake. So without further ado, let me introduce our first two witnesses. And I'm pleased to say we have with us Dr. Pippa Wells, who is the Deputy Director for Research and Computing and Management Liaison for the United Kingdom at CERN, and has worked at CERN for many years, and Christopher Hartley, who is the Head of Industry, Procurement and Knowledge Transfer at CERN. Thank you very much indeed, both of you, for coming to give evidence. Perhaps I can start with Dr. Wells, and in the spirit of an introduction, just tell us a bit about CERN and what is the UK's contribution to it.
Thank you. So CERN is the world's largest laboratory for particle physics. You've already mentioned it's our 70th birthday this year. Our facilities straddle the French-Swiss border near Geneva in Switzerland. So the original headquarters was in Geneva, or outside the city near the French border. What we're trying to do is understand the most fundamental particles, the smallest particles that make up matter. We're trying to understand the forces that the interactions between those particles, and we're trying to understand how that relates to the evolution of the universe, so from the Big Bang to what we see today. The UK was one of the 12 original founding member states of CERN back in 1954, and is now one of the 23 member states, and it's our second largest contributor. So the member states contribute in proportion to their net national income, and the UK contributes at around 15% of the total CERN budget, which is 1,200 million Swiss francs per year. So for the UK, that comes in around 160 million pounds per year, depends a bit on the exchange rate. The idea of CERN, when it was founded, was to do science for peace. Europe was emerging from the Second World War, and the idea was to do projects that were much bigger than could be afforded by a single European country, possibly also to attract people back to Europe who might have left for the States during the war and in the aftermath of the war. And that's still the case today. We're doing projects that are funded by our 23 member states that couldn't be done by a single European country. CERN's best known for its fundamental research, but it's actually really an engineering lab. People say, I'm not a physicist, I can't work at CERN, but it's really the engineers, the technicians who design and construct and operate our facilities that are the core of the people actually employed by CERN. CERN builds and operates particle accelerators, which bring particles very close to the speed of light, very high energy, and then they either hit a target or they're maneuvered, the beams of particles are maneuvered to collide head on. And our flagship accelerator, the Large Hadron Collider, does exactly that. It collides bunches of protons, which are the nucleus of hydrogen atoms, head on, and then we have to observe the products of those collisions. So it's Einstein's E equals mc squared in action. The very high energy of the particles is converted into new particles, which fly out from the interaction point, and large particle detectors surround those interaction points. That's another place where the UK has a very large contribution. We have a community of 12,000 scientific associates. These are the scientists, the users who come to CERN to do experiments. The people employed by CERN are just a small fraction of the people doing the experiments. So we have, from the UK, from UK institutes, about 900 of the scientific users. And if you compare that to the member states alone, there are 7,000 users from member states. So the UK really does have a good fraction of the users coming from member states. I've mentioned two technologies, the accelerators and the detectors. The third very important technology for CERN is computing, information technology, because we produce very large volumes of data which need to be analysed.
Excellent. Thank you very much indeed, Dr. Wells. Just in terms of the subscription, you said it equates to about £160 million a year. In addition to the subscription, the taxpayers' funds through the Science and Technology Facilities Council contributes towards experiments, and that's to the tune of about another 20 or 30 million pounds a year. So we're talking about an annual investment of about £1/5 billion a year, which is pretty substantial in science funding terms, in any terms. Good. Thank you. Let me go to some questions from my colleagues, starting with Tracy Crouch and then Rebecca Long-Bailey.
Thank you very much, Chair. That was really interesting introduction into CERN. But what I want to ask is why is that? Why is it important? Why does it matter? What does it contribute to society?
Scientific curiosity it's a fundamental element of humanity. People look out at the stars or they want to understand how things work. And progress has been driven by fundamental research. It's not research that's done for the sake of developing products for industry. It's been gradually over the centuries even understanding how things work, how science works, and then that can have knock-on effects. I'll give you an example. Einstein's theory of general relativity, which takes Newton's gravity and then extends it to understand, the big-scale structures. It was a fantastic theory, but if we didn't have Einstein's theory of general relativity, GPS systems wouldn't work. It's actually needed to correct the time signals from the satellites for the effect of different gravity on Earth and in the satellite orbit. And so we maybe don't know right now what applications the fundamental science of CERN could have in the future, but we know from the past that these things tend to eventually develop applications. More importantly, in addition, the technologies we develop then go off into wider society, and they're used in all manner of different applications, medical applications, for example. Another element of putting back to society is the science at CERN is one of the things that young people find exciting. Particle physics and astronomy is one of the reasons kids go into then studying STEM subjects, and we know we need people with STEM experience. They maybe don't ever come to work at CERN, or maybe they come to CERN and do a doctorate. We have something like 3,000 people doing their doctorate degree at any one time with the Large Hadron Collider experiments, and about half of them then go back into industry. They've had an international experience, they've learnt some high-tech stuff, maybe advanced computing, maybe detector technologies, and then they take that back into wider society. But I think we must accept that a rich scientific program needs elements of fundamental research as part of that full picture, and that's really CERN's primary aim.
You use the phrase scientific curiosity at 180, 190 million pounds per annum. That's quite an expensive investment in curiosity. Certainly as a former minister, we had to apply an ROI on all of our spending, a return on investment of all of our spending. Is there an estimated ROI on the £190 million per annum?
There have been studies done for the UK for the impact. I can't give you an exact figure. The methodology gets difficult, putting a currency value on a scientific research paper, for example. There are different methodologies that people try to apply.
Thank you. Mr. Hartley, could you tell the committee what role does CERN play in training and employment opportunities for UK nationals?
Certainly. So there is quite a large variety of schemes that we have. So from the doctoral students, but also we take, for example, new university graduates. We have a graduate program. We also have a lot of outreach to schools. We have many schools. I think it's 500 school visits per year from the UK, that sort of number. And also we have a program for what we call training the teachers or teaching the teachers, so that physics teachers or scientific teachers from the UK can attend specialised schools in CERN to help. So it covers the various ranges.
Thank you very much indeed. Rebecca Long-Bailey, then Chris Lux.
Thank you. My constituent, Dr. Connor Fitzpatrick, who's watching today, was able to obtain his prestigious academic position at Manchester University as part of a European research grant, which was based on the research that he carried out at CERN. His story, sadly, is unique. What additional measures in terms of outreach does CERN conduct, and how does this inspire people of all backgrounds to pursue STEM and become another Connor, Dr. Wells?
We put a lot of effort into identifying UK nationals or people employed by UK institutes at CERN from all sorts of diverse career paths, be it apprentices, technicians, and they volunteer to be ambassadors, to go back to their school or to their university college, give presentations, explain the range of opportunities available at CERN. We're keen to get the numbers up of people taking advantage of things like our apprentice courses, technical student courses, because they're basically the pipeline for then feeding into the higher level positions at CERN or in UK universities. And we're conscious that an undergraduate population or a school population turns over very quickly. You can't do it once and say, right, we've told the university of somewhere or the college of wherever. You've got to keep going back. And it's also nice if the younger people go back. They, not me. Look at this young technician or who's been to CERN. They're excited by CERN, and you can do this too.
Mr. Hartley, is there anything that you'd like to add to that?
No, I don't think so.
Okay, moving on to procurement. Mr. Hartley, how does the UK compare with other international collaborators in winning CERN procurement contracts?
I would say reasonably well. There are two views. I'd like to present it in two ways. So overall, the UK, we divide our procurement contracts basically into two large categories, what we call our service contracts and our supply contracts. The service is a typical engineering or other services to make the institution and all the experiments run. And there the UK is placed fourth and consistently fourth between our, as the chair introduced, our 23 member states and the 10 associate member states. And then in the supply contracts, the UK is currently fifth in the amount of the contracts that are awarded, or the payments made to UK companies more accurately. What I would say is that historically, whilst the positioning has been is okay if you look at it from that perspective in terms of numerical financial value, it's been far below what I would say CERN and from the UK perspective we would want to have. And we have been working with the UK government representatives, particularly our colleagues in STFC, to improve that. So over the last 2 years particularly, we've seen very significant growth compared with the payments to UK companies on the supply contracts in 2021. We had a 46% improvement in 2022 and approximately 45% improvement in 2023. So if you can combine those together, between 2021 and 2023, we doubled the payments to UK companies under supply contracts.
Thank you.
Thank you very much indeed. Chris Clarkson and then Carol Monaghan.
Thank you, Chair. Mr. Hartley, if we can stay with the same theme. Obviously, you say the UK does reasonably well with overall the supply, but obviously, given the numeric value of the cash value of what we're putting in, we would obviously like to see more of a return on investment. So what sort of engagements taking place with UK businesses to drive more R&D and commercialisation of the research? And I appreciate not all of it can be commercialised yet, as Dr. Wells said. Some of these things we'll find an application for later. But what engagements taking place with businesses at the moment?
I would like to draw a distinction first, if I may, between what CERN does with all its member states and then say a few words about the particular focus we have on the UK because the improvement of the UK situation is so important to us. So CERN, we have a whole range of activities that we We partake into encourage interactions with business. All our member states and associate member states have industrial liaison officers who we work with on a very regular basis to ensure that they are aware of the upcoming commercial opportunities and that they form the bridge with companies and organisations in their member states so that they are aware of CERN specific procedures and how to work with CERN. That we do with all member states. We also organise welcoming days for companies to come and visit us, and we do days focused typically now on particular themes. So we may be saying we're very interested in purchasing new cryogenic systems, so we would invite all member states to be aware of our upcoming needs. Then particularly with the UK, because it was a priority from the UK side, also from the CERN management side, we have put in place some very specific actions with the UK. So we have a member of my team has a weekly meeting with the UK Industrial Liaison Officer to make sure that we are aware of the opportunities coming available for commercial companies so that we can have early identification and outreach to companies that we believe may be suitable suppliers for those particular contracts. In addition to that, we do a monthly strategic meeting to look at what are the barriers, whether they be perceived barriers or real barriers, which make it particularly difficult from UK companies' perspective to work with CERN and see how we can address those barriers. And then in addition to these outreach that we do, within our procurement system and our procurement rules, we have been using a particular element which is called the limited tendering. So when a country is doing particularly badly in our procurement and has a lower coefficient, we are able to use that to target procurements to that member state, assuming that we can generate sufficient competition, which when the UK was lower than it is today, we were able to do, particularly in the IT domain, and that's part of the improved results that I just mentioned earlier, with the significant increase in the last 2 years, is using specific tools to assist the UK.
Notwithstanding that targeted process, obviously the sort of the general procurement system is an open one. Is there any particular reason CERN uses that rather than, say, for example, one that's linked to contributions like ESA uses, for example?
Oh, if I compare with the European Space Agency system there, where they are looking at whether they have a concept of a sort of fair return or just return on each of their major projects. So firstly, I would say it's important to understand that they do it across major programs or major activities. So that is divided between different missions. So that works very well, I think, for them on those individual missions. And it allows them within those individual programs to divide the work up equitably in terms of relatives to the contributions. Of course, that does also mean that they're often working with a sort of prime contractors who themselves, then there is a kind of a transfer of some of the knowledge and the decision making to the prime contractors. So the prime contractors are taking, whilst many of such agencies such as ESA themselves have great expertise, they are relying on their prime contractors to work with them to share the work out between them. In CERN, we retain the prime contractor knowledge, the engineering knowledge, as Dr. Wells mentioned. We're very much an engineering laboratory, so a lot of that knowledge is held within CERN, and we believe that it's interesting to retain that knowledge. Then we believe that within any procurement system, one is always balancing various parameters of what exactly you're trying to achieve. Typically, cost, schedule, quality, you're balancing those. When you introduce a return contribution coefficient as well, there is a danger that you have to sacrifice one of your other parameters in order to ensure that there is a balance on the return. You may then be sacrificing one of your other parameters, for example, potentially increasing costs or reducing quality, because you have to award contracts in a certain way rather than taking the best that the market has to offer at the time.
It's the old adage, you can have quickly, cheaply, or well, but you can only pick two of them.
Yes, I would say, but we're sort of adding an additional one, which is, but everybody has to get a fair share of the cake. So.
Excellent. Thank you very much.
Thank you very much indeed, Chris. Just before I go to Carol, when we were a member of Horizon Europe, the scheme, we took more out than we put in because the prestige and the quality of British science was better than average. Here we have a situation in which, notwithstanding the prestige and the excellence of British science, we've heard in the answers to Rebecca and to Chris that on procurement, technical UK companies are underperforming our contribution. When it comes to people working at CERN, we contribute about 15% of the budget, and we have only 7.5% of those employed. So from a situation previously in other European and international collaborations, we get more out than we put in. We get far less. Surely there's a big problem here.
Well, as I hope I've said in my answers, in the procurement side, we're very aware of this, which is why we have dedicated initiatives. And I think to say that we've had a 100% improvement in the last 2 years, to me, is a clear indication that we agree with you and we are addressing the problem.
And in terms of employment, I don't know whether perhaps Dr. Wells might be...
In terms of employment, we're trying to understand why is it that UK nationals are not applying, or if they are applying, why are they not necessarily being successful? It's a multi-pronged problem. I could say, though, I've already mentioned that from the point of view of the scientific users, the UK science community are they're getting their fair share of the CERN facilities. We also do rather well in leadership positions in terms of directorate, department heads, head of the legal service, to give another example. But we need to keep filling that pipeline so that we gradually can increase the staff numbers in the coming years. It's something we want to work on together with STFC.
Thank you. I think Catherine just had a quick supplementary.
Yeah. I just wanted to, sorry for being scientist, I just wanted to enumerate this doubling. So, 45%. So what financial value have we gone from in 2021 to 2024?
So in Swiss francs terms, in the supply contracts in 2021, it was just over 11 million Swiss francs was paid to UK companies, and it's well over 22 million were paid in 2023.
So it's a significant, but it's probably only, a 10-ish teens% of the overall annual contribution to the UK. Yeah. Just one more, if I may. You mentioned the UK Industrial Liaison Officer. That sounds like a really sensible innovation. I just couldn't work out, who does he work for? Does he work for you guys, or is it she?
No.
Or
he works for STFC.
Yeah.
And is based at STFC, but interacts directly with us. They also have some representation in CERN.
And how does that role then get to industry? Do you see what I mean? Is it linked into the Department of Business? Is it linked into a catapult? Is it linked into the industry bodies?
Oh, it's the STFC function. They liaise with DCIT, obviously, and they are working directly with UK supplier companies. For example, they organise roadshows. They've performed regional roadshows where they reach out and they have presentations about CERN and the upcoming opportunities, and contact industry in the specific areas.
Superb, right. So if any company is watching this, straight to an STFC roadshow to take advantage of CERN opportunities.
Absolutely.
Yeah,
And that's paid for from the STFC budget, is it? So that comes out of the research budget?
I don't feel qualified to comment on how it's paid within STFC.
Thomson, later, but that's not from the CERN subscription. We're paying extra from UK funds in order to remedy a problem in CERN, as we might see it, or think about it. But there's perhaps one for Mark Thomson to be fair. We'll come to him later.
Yes. We also do run events at CERN, which CERN is funding. So yes, there's something coming out of the CERN budget also but we need to get companies on site so they meet the engineers who are actually have the deep knowledge about what's needed, so they can have a proper conversation on the technical details of the specifications of calls for tender that might be coming up.
Thank you very much. Carol Monaghan, then finally in the session, Graham Strew.
Thank you, Chair. Dr. Welsh, you've highlighted the benefits and the benefits of doing blue skies research and research for research's sake. I suppose what we're trying to get at is this value for money, and are there other places that research for research's sake could, I suppose, produce better economic outcomes? I mean, 15% of CERN's budget comes from the UK, but we're hearing about these the lack of procurement coming to UK companies. Maybe if I turn to Mr. Hartley, is it UKRI and UK government that should be doing more in order to get more companies winning contracts there?
So my view is that it's very much a three-party approach. So we in CERN need to do the outreach. We need to ensure that our procedures, the information we make available, is transparent and clear and is a level playing field. So that's very important to us that we do that. We need to work with UKRI, with FTSC, and then there is the industrial component as well, that the UK businesses need to have the appetite to work with us. They need to understand the benefits. So that's what the roadshows that I was just referring to are very important, that we explain to them how we do business, because when we have our own specific procurement system, there is always the risk that there are certain things in there that they look at and say, oh, that's too complicated, it's not worth it, oh, it's only one contract, and they need to understand the potential long-term relationships. So an organisation that's 70 years old, very often what we see is that our suppliers, once in place, they continue to be suppliers, they have repeat contracts.
Just looking at this, France seems to do quite well from contracts. Obviously, geographically, it's well placed. But how much does France contribute? Would you know that?
Yes, the French contribution is slightly less than that of the UK. They pay about 14% of the CERN budget, if I remember correctly. What I would say, I think you will find you probably a better place than me to comment on it, but I understand that in many international organisations, the host states and geographically close states have a significant advantage. There are many things here. When we're placing contracts for maintenance of the roads on site, for example, for re-roofing, we're extremely unlikely to convince a UK company to set up an operation close to Geneva to re-fence the site. That tends to have a very natural influence to be from France or Switzerland, the local economies.
If we're talking about deep science and engineering, that could come from other places.
Absolutely, yes.
Dr. Wells, sorry.
The key product of CERN is scientific results, publications. Each of the large experiments at the Large Hadron Collider has put out by now hundreds of papers, and UK scientists are signing those papers. And as I think I mentioned before, it's difficult to put a monetary value on that, but it's really pushing the frontiers of knowledge. This is our business, and we're doing that, and the UK is a key partner in achieving that. So if you focus entirely on the industrial procurements, it's perhaps leaving aside what's the actual main product of the organisation.
Maybe turning to that and looking at that in a bit more detail, Dr. Wells, could you tell us a bit about the Future Collision Collider? What is it? Does this project have widespread support from the physics community, and how is that going to benefit science and wider society?
The present research at CERN has, over the decades, discovered various particles which are components of our standard theory that we call the standard model of particle physics. And it does a fantastic job of explaining and predicting the results of collider experiments, but it only explains 5% of the mass and energy in the universe. It has various other problems. We don't understand why there isn't the same amount of matter and antimatter in the universe, why there isn't enough matter left over to make committee rooms and so on. So we want to understand more. We want to understand how to advance the missing parts of the theory in order to have a better overall picture of the evolution of the universe. To do that, at the moment, we have a project to upgrade the intensity of the Large Hadron Collider to the so-called high luminosity Large Hadron Collider, and that will continue running until 2041, and it started operation in 2010. So these are decades-long projects. Before the Large Hadron Collider, there was a previous collider in the same tunnel called the Large Electron-Positron Collider, which started in 1989. Now, I'm telling you this because we now are in the process of a technical and financial feasibility study for a future circular collider, FCC. And that program will last something like 50 years. It will start about 20 years from now, if it's approved. And it would start with a machine, an electron-positron machine, which would measure in extreme detail the properties of the heaviest fundamental particles that we know. It would try to see if their properties are exactly what's predicted by the standard model, or if they're subtle differences that give us a clue as to what's going on beyond. And then in a second phase, we could put a Hadron Collider in the same tunnel. So the technical feasibility study in progress had looked at something like 100 different possible layouts for the future circular collider, and has chosen one that seems to be the most beneficial in terms of satisfying all the requirements of the 2 phases of the project. It has a circumference of 91 kilometres. It's roughly 200 metres under, well, it's on average 200 metres underground, because it has to be in the good quality rock for tunnelling, which is the molasse in the Geneva region. It also has to get under Lake Geneva and under the Rhone River, so that's what sets the depth to be able to avoid these obvious constraints. The placement has also looked in detail at using as much as possible of local infrastructure and existing CERN infrastructure. So, for example, where can we connect to electricity supplies that are already existing, to power converter stations that already exist? What's the minimum amount of new road building that would be needed? So all of these environmental considerations have fed into finding the optimum placement and length of this tunnel, and also being able to connect to the existing CERN facilities that would help in preparing the beams to then go into the big new collider.
I mean, from what you're saying, we can understand the benefit to science from that deep sort of understanding and discovery. What about society? Is the societal benefit about the kind of spin-outs and the engineering advances, or is there something else that society will get from this?
I think the societal benefits will continue in the same manner as they have now. For example, we need to develop new high-field magnets for the eventual Hadron Collider option. So research and development on how to make high-field magnets, not necessarily at liquid helium temperatures, but maybe higher temperature superconductors. If you can achieve something like that, the same technologies can then be used to make other
energy networks, for example.
Energy networks from equally superconducting, high-temperature superconducting cables for energy transmission. Yeah. You also asked about, is this widely approved? Yeah. And I wanted to explain that the
I'm just conscious of time, Dr. Wilson. The chair will start getting upset.
In brief, the strategy for particle physics in Europe is set by an exercise called the European Strategy for Particle Physics, which was first completed in 2006 and is updated every 6 to 7 years. This feasibility study was one of the was the top priority of the previous update, and it will be an input to the next update. And this is a bottom-up exercise involving thousands of scientists, not just particle physicists, but also astronomers and nuclear physicists. So it has very widespread support in the scientific community.
Thank you. And I think, Mr. Hartley, you want to say something, if you can, in 10 seconds. That's great.
Just very briefly to say that when we talk about energy networks, it's not a hypothetical concept. We are working today, we have our knowledge transfer agreements. We're working with companies who are investigating. For example, in Scandinavia, a major problem that they have is with offshore wind farms. There's a tremendous loss of electricity before it's delivered to the end customer. We're working with a company right now to use the same technology Dr. Wells was referring to improve their transmission lines. We're also working with Airbus, who are working on zero emissions aircraft, hydrogen-powered aircraft, and they need superconducting cabling technology in their aircraft in order to keep the weight down. So those are real projects that we're working on today.
Thank you.
Thank you very much indeed, Carol. Can I just check, is the funds that are being used to develop the case for the future collision collider, are they coming out of the current CERN subscriptions?
Future Circular Collider. It's a collaborative effort, so it's partly studies done by CERN, but it's, again, like all of the CERN collaborations, it's something like 130 different institutes involved.
It hasn't been decided that it's going to be embarked on, but so funds are being taken from funds that have been committed to current experiments to make the case for a future piece of infrastructure. Is that
well,
fair
the
summary?
the CERN medium-term plan for the budget includes elements of research and development and studies for the future. It has to, otherwise you're not ready for when you finally come to be asking member states for approval.
And that plan is approved by our member states.
All right. Graham Stringer, finally.
You've helped us with some information about the Future Collision Collider. Why wasn't the mid-term report on it made publicly available?
The feasibility study is a 5-year study which will be completed in 2025, at which point it will be made public. This was a scrutiny of the progress so far to be sure that it's going in the right direction. And a lot of the input is available on the CERN website, on the Future Circular Collider website, but the overall report was not made public because we're still working on exact details of the geological surveys and some of the negotiations with the host states and so on. So this was why the full report was not made public at this stage.
But would it do any harm to make it public when you're talking about such large amounts of public money? Isn't it better to be as transparent as possible?
Indeed, and CERN does have being open as a fundamental part of its DNA. The issue here is that it's a work in progress. Some of the numbers are preliminary. We did not want to put it out at this stage until we can really be sure that the study has been thoroughly completed.
Just going back to the physics, I've always thought it rather amiss of physicists and astronomers to miss 95% of the universe. To simplify it in the way that the objective of the Large Hadron Collider was always explained to the world, that you were looking for the Higgs boson. Are you looking for... Will this project be a success if you find dark matter? And is the other thing you're looking for an explanation as to why we're here, why there is matter and not antimatter?
The Large Hadron Collider was addressing several questions. It was, is there a Higgs boson? Yes. Is it exactly what we predict in the standard model? That's a work in progress, measuring its properties more precisely. It will continue. There are experiments at CERN, at the LHC, and at another facility trying to understand matter-antimatter. We know from the way galaxies move and from large-scale structures in the universe, there must be something else exerting gravity that is not visible stars. So dark matter isn't some speculation. There is observational evidence that there must be either dark matter or something else playing the same role. We did not yet find any direct signal for dark matter at the Large Hadron Collider. So we're now having to explore more theories, and if we don't actually see it, that's actually a result. If you don't find it, you exclude a lot of possible models, and you really constrain the theory explanation that you'll have to come to in the end. So it's a subtle thing, but not finding something is already giving you an awful lot of information.
So that is one of the objectives of...
We can't say we will find dark matter because we don't know what it is. We don't know how strongly it interacts. So we're doing configuring experiments in as many different and clever and cunning ways as we can to make sure we haven't missed a signal. And we're exploring. If we knew what the answer was, we wouldn't need to do the experiment.
I understand that. I mean, there are two very big questions that for any large amount of public money to be spent on science. One is the actual objectives of what you're looking for at that particular time and what you understand and why you're going in that particular direction in that field. And the other is how you compare and contrast and argue against investing in other pretty fundamental parts of science. The origin of life might be one, or consciousness, really fundamental questions in science that are yet to be answered. So how would you, in simple terms, explain or justify both the particular niche within physics and against other fundamental questions?
My view is that you need a balanced portfolio. You have to decide what are the important questions for humanity and address several thrusts. You don't say, I'm not going to do life sciences because I want to do physics. It really, you need the broader
That's almost self-evidently true, isn't it? But I'm asking really how you justify the quantities of money, very large amounts of money for CERN as against potentially very large amounts of money for the study of consciousness.
Study of consciousness.
Or the origin of life, you know, the fundamental question.
As I said, I'm sorry to repeat myself, but I feel these are all very important fundamental questions to me, and the physics, the origin of the universe and so on has always been something I've been interested in, and it is something that inspires young people. It's not niche from that point of view.
Maybe I'd like to add something. With the very challenging conditions that we create in CERN, in our accelerator, in our experiments, when we talk about the companies working with us, there's the numerical, the financial value of the contracts that they're receiving. Also, our requirements are so specific and so challenging. What we find is that the vast majority of companies that work with us say that they improve their skills, that they improve their products, that it opens additional markets for them, because sometimes by setting really challenging requirements for very specific conditions, it really gives a badge of quality. It gives a new level of reference for those companies when they're working in other areas. So by taking on the biggest questions, it helps you to develop your capabilities for other industries.
Thank you very much indeed, Graham. Given how fundamental these questions are, should they not be investigated at a global level in terms of future facilities? In other words, should the future collider not be a global endeavour rather than a CERN, principally European endeavour? A bit like the Square Kilometre Array in astronomy is a global initiative, is it not?
CERN is a global endeavour at this stage. The people coming to do the experiments have 110 different nationalities. If I take the example of one of the big Large Hadron Colliders experiments, it has of order 180 universities and labs collaborating from 40 different countries. The scientific collaboration
does the
span
US
the globe.
Subscribe to CERN?
It does not give a regular subscription, but it does
That's
pay,
what I mean, really. Should superpowers like that be included?
It does pay membership fees to be parts of the experiments. It has made extremely significant in-kind and cash contributions to the Large Hadron Collider. We have a kind of reciprocity arrangement. CERN is participating in constructing some things for the neutrino physics program in the US. So it's a partnership, and definitely we would hope that partners such as the US would give a significant contribution to the Future Circular Collider. There are US scientists taking part in the feasibility studies, some of the specific magnet R&D, for example. It's based in Europe. It's originally a European organisation, but now it really is truly global.
I'm very grateful for your evidence this morning. We should go on to the next panel, but Dr. Wells, Mr. Hartley, thank you very much indeed for coming to give evidence in person. Let me introduce our next panel of witnesses. We have in person joining us in the committee room Professor Sir David King, known to Parliament over the years extensively as a former government chief scientific advisor, and was the government's permanent special representative for climate change between 2013 and 17, and was the founding director of the Smith School of Enterprise and Environment at Oxford. Sir David, thank you very much indeed for coming. And joining us virtually from Germany, I'm pleased to see on the screen Dr. Sabine Hossenfelder, who is a researcher at the Munich Center for Mathematical Philosophy based at the Ludwig Maximilian University of Munich. Thank you very much indeed, both, for joining us. Perhaps I can start with Sir David and You, I think, have expressed some concerns about the next phase, the proposed collider that has been referred to in the first panel. Would you say what your concerns are?
Yes. Basically, my main point is the opportunity cost to other areas of research. And so if I look at the various curiosity-driven research projects, and I've been involved in quite a few, for example, the Kennedy Apollo program, which I was directly involved in for a while, and that program was aimed at getting a man landed on the moon, a person landed on the moon, and that was achieved. And now I'm going to draw a strange comparison with the 3 billionaires in the United States who are planning once again to put a person on the moon. And I actually am going to say the opportunity cost of this is massive, and we are not going to see the benefits from repeating what has already been done in this way. Curiosity-driven research, if I can move on to other very good examples, we've got DNA. That was curiosity-driven. That was curiosity-driven in my university in Cambridge by the challenge by various biologists to say, surely these things in biology have structures. And there was a big sort of thought around that, no, they were too plastic to have structures. And then X-ray diffraction was utilized, working alongside physicists in Cambridge, totally interdisciplinary, and they emerged finally with the structure of DNA. That was curiosity-driven, but I'm going to say, look at the follow-through on that. Right? It's just been enormous. The benefits to humanity from an understanding of not just what DNA is, but its structure, and then tackling various medical problems in this way. If I can take you to my own field, which is solid surfaces, when I moved into this field, and I'm going to tell you this is 50 plus years ago, there was no understanding at the atomic or electronic level of the structure of a surface. Surfaces were challenging because it's a breaking point in symmetry. And I took on this problem alongside, I think, half a dozen other global leaders. And what emerged from that was a complete understanding of surface structures. And in amongst those surface structures, silicon, and of course the whole internet revolution depends on having computers. And these computers are all driven by not transistors as we had in the old days, but tiny little devices that have megabytes on them. So what we've seen is curiosity-driven research, and I'm stressing the fact that what emerged from this was not just curiosity being understood, but the application of those discoveries. Now, of course, we're all delighted, and take me back to when I was a young man. I was as interested in astronomy as I was in any other aspect of science. And so, yes, it does provide that sort of interest for young people. Excitement draws you into the field, and then you can be productive in whatever area. I'm just going to say the excitement around the discovery of the Higgs boson, that might in itself have been justification for the enormous amount of money spent to build that Large Hadron Collider, which is 77 kilometers in circumference. I was down there, privileged to be down there, seeing it under construction. It is just an amazing piece of engineering and physics. But then if I ask myself, well, Higgs did predict the boson, and then it was discovered, and that's a very satisfactory way for science to proceed. But what benefit comes to humanity from this discovery? It is pure curiosity-driven. And the higher energy you go to, the more particles you will discover, and yes, it will provide a more complete understanding. And I was talking about the Large Hadron Collider as really being the last chance for this community. to do some significant work, because otherwise now we go from 77 kilometres to 91 kilometres. What's the end point? There's no end point, because energies can always be increased, and there will be new discoveries in that process. So I'm really concerned about the opportunity costs from UKRI's expenditure. And what I'm really going to talk about, if I may, for a moment. Yeah.
Let me bring in your fellow witness, and then we'll have some other questions that will enable you to expand on that. Perhaps I can ask Dr. Hossenfelder. You've written in public print some concerns, which I think are kind of allied to what Sir David has said. But just tell us your concerns about the focus of expenditure on the proposed new circular collider.
So I agree with what Dr. Wells said earlier, that progress is driven by fundamental research. I entirely agree with that. But there are at any moment in time many things, many areas in which we could do fundamental research. And I think we have to be very careful about choosing the right ones. Because as Dr. King just said, there's always opportunity cost. And what I'm personally very worried about is if we spend a huge amount of money building this bigger collider, it's going to attract a lot of people working in this discipline, and those will be intelligent, smart people who are not available to work on other things where they might have a bigger societal impact. There are only so many skilled people who also have the interest to work on this stuff, and they'll be drawn from related areas like material science, artificial intelligence, climate physics. There'll be fewer people available for those. So Dr. King just said if we go to higher energies, there'll be more particles discovered, and I think particle physicists wish that this was true. But there's absolutely no reason for that to be the case. And it's true that we do have some observations out in the cosmos that are normally attributed to dark matter, but for one thing, it's not sure that dark matter actually exists, and even if it exists, it's not clear that it's made of a particle, and even if it's made of a particle, it's not clear that this bigger collider would actually find the particle. I would also want to remind you that pretty much all particle physicists I were pretty convinced that the Large Hadron Collider would actually find the particle that makes up dark matter, which has not been the case. Now the predictions have been moved to the next bigger collider, but there's no reason that this should find the particle. When it comes to the other questions that were alluded to, like what's dark energy and the matter-antimatter asymmetry, I think the chances are even smaller that this new collider would tell us anything about it.
Thank you very much indeed. Let's go into a bit more detail on that. Stephen Metcalfe has some questions so to do.
Thank you. Yes, really, Sir David, you said that it would be reckless to spend 12 billion on a future circular collider. I think you told the BBC that. What would you spend it on?
Thank you. Wonderful question. I'm going to say that I'm now supporting Tim Palmer, the professor of atmospheric physics, theoretician based in Oxford, who in 2010 published a paper saying, why aren't we spending more money in understanding the risks associated with climate change? I'm just going to, if I may, say a little bit to back this up. We've had a 37-year experimental observation of ice melting from Greenland, which has been recently published. And what this concludes, and this is an extraordinarily detailed study, for example, double satellites involved, it's been very expensive. But the discovery is that over the 37 years, the loss of ice has averaged 30 million tons per hour. And over that 37-year period, it's estimated something like 1 trillion tons of ice have been lost from Greenland. Now, what this very much looks like, and scientists are cautious about their conclusion, is that the ice on Greenland is now melting irreversibly due to climate change that has already happened. And so when we are looking at challenges facing humanity today, this has surely to be the biggest challenge, the impacts of climate change. So the melting ice from Greenland, when it has all melted, global sea levels average will have risen by 7.5 meters, 24 feet. We certainly wouldn't be sitting comfortably here at that sort of sea level rise. So it may take 200 years, but I think we have a need to worry about a distant future. If we can look back at our civilization's history over thousands of years, we surely have to look beyond 50 years. But even in 50 years' time, it now looks very likely that loss and damage from the impacts of climate change, in particular what's happening around the North Pole region, that the impacts are such that we are losing at least $250 billion a year in loss and damage that we weren't losing just 10 years ago. So this is the big challenge. So what do we need?
Briefly, if you would, Sir David, we've got quite a few more questions to get through.
Yes. So what we need is a CERN for climate change, so that we have the ability, for example, to predict for every part of the world with a detailed capability what the challenges will be. Every part of the world is going to be challenged in a different way, so we can adapt to those processes, but much, much more than that.
Thank you.
Okay, so thank you for that. So this is public funding going to go towards potentially funding this or not. What process do you think governments, funding bodies should go through when they come to considering investment in large infrastructure, scientific infrastructure in the process, to make sure that we are getting the best impact? Now, it's not always about return on investment, but return can be intellectual as well, to ensure that we are spending our money as wisely as we can.
This is precisely why I very much welcome what this committee is investigating, because normally we follow precedent. Right, so here we have a community of, 11,000, 12,000 scientists who have put a very good case forward, although that case is questionable, as we've just heard, but have put a case forward for continuing with their work. And this is a very difficult question. Can we actually say, no, that's it? The United States did. They were in the particle physics arena and withdrew when they thought there were other opportunities in the science area. So I do think the Select Committee has a very difficult task, which is to look at this as an opportunity cost, because I don't think in the situation in the world today, in the way our biosystems are being challenged, in the way that our entire civilization is being challenged, I don't think this is really fit for purpose, because it isn't giving us the opportunity to manage these crises. It's looking askance at something that is fascinating, absolutely fascinating, but not going to provide solutions to the problems we're faced with.
So, okay, we may be part of that system of deciding funding. Who else should be involved? I mean, bear in mind, I think it is right that politicians don't make specific funding decisions. They can make recommendations. A panel of senior scientists, a mix of business people and scientists and politicians. How do we make these decisions? Because it's big amounts of money. You've highlighted the biggest probably threat that the planet faces. We know we need to do more. It's a balance.
I mean, your question obviously is the big one. You can put in a recommendation, but you're going to say, well, Britain is one part of 23 nations supporting this. However, I think it's got to be recognised that the British voice in science and the future for science is very strong. It still is very strong. We've got a historical base here, and people do take notice of what we say. And whatever you say, what the Parliament of Britain says, is going to really have an impact on this issue. It's not something we should duck, because each one of us is responsible for the decision making. Now, obviously, I would like to see the same discussion happening across Europe and the contributing nations. And we ought to be stimulating a discussion of that kind. Give it back to the science community, and I believe they will simply say, let's take precedent, right? Which is the way it has normally operated. So there is that real risk that we simply follow precedent. By the way, can I pick up on what our colleague has been saying? It is also an opportunity cost for these brilliant minds being drawn into this research instead of going into discovering the solutions to problems that face us in the future.
Thank you. Can I have one final
and
short
Carol,
question? So you were the Chief Scientific Advisor to the government from 2000-2007. If you were still wearing that hat, would you be quite as forceful in your views as you have been recently? Would you be advising the Prime Minister not to spend 12 billion on this and to do something else?
So the answer is, I think I was quite forceful when I was Chief Scientific Advisor, and I would. My position is that I'm always true to myself. So I will always give advice that I actually believe is the right advice. So I would do exactly that.
Thank you very much.
Thank you very much indeed. Some supplementaries, Carol Monaghan and then Catherine Fletcher.
Yeah, thanks, Chair. We're the Science and Technology Innovation Committee. We are all for spending money on science. We're all for supporting good science, and we all understand the benefits that science can produce. Is there a danger if, in a hypothetical future, that funding for CERN was reduced? Is there a danger that that money would not go into climate research and, in fact, would go to some other pet government project?
That is a very difficult question. I can't decide how this money should be used because others will make that decision, and there is a very real probability that the money will be dispersed amongst various different existing channels of funding. What I'm trying to do is to say...
Or not at all.
Or not at all. It could even mean the government withdrawing that sum of money from science research, which I think is what you're suggesting might happen, which would be disastrous. So I think, however, this committee, I shouldn't say what you should be doing, but you do need to be looking at a given budget and how that budget should be spent, not suggesting that maybe if we don't spend it this way, it'll disappear. I think your point is still a good one.
In fairness, we do that as well, but we're not the people that hold the purse strings, unfortunately. Or maybe fortunately. Thank you, Chair.
Just on that point, Dr. Hossenfelder, from an international point of view, the point that Carol Monaghan was making was that you might lose this. You talk about an opportunity cost, but actually it may go to other valuable parts of public expenditure, schools, hospital and the like, rather than science. Do you assess that as a risk internationally for other subscribers other than the UK?
Yes, people constantly warn me about this. It's definitely something that people worry about also in other countries. Though I have to say, this is a very difficult decision to make. Maybe it's actually more important to build schools and have some program for getting people out of poverty. So this is not really something that I can speak about a lot. So I come at this very much from the perspective of a scientist, and I just think that at this moment in time, there are other research areas in the foundations of physics where the money would be better invested.
I see. Very good. Catherine Fletcher, finally, in this panel.
Thank you very much, Chair. Dr. Hossenfelder, I confess I went to CERN, I bought the standard model fridge magnets. I'm captivated by the science of it, the opportunity to understand exactly how these open questions are. But as a parliamentarian, I have to ask and investigate some of the more difficult questions. And there's always a dark corner of the internet where you can find something. But I did come across your material. And if I'm right, what you and others are saying, particle physicists talk about answering the big questions, but the record of success is not there outside of the Higgs boson. And that, so supersymmetry, for example, seems to have gone, dark matter has not been discovered, and that actually some of the rhetoric about what large colliders can achieve scientifically versus the experiments that are positioned within them and their ability to answer the questions. And I just wondered if you could elaborate a little bit on the gap between the joy of it and your concerns about the actuality of it.
So particle physicists are very interested in particle physics. I speak to a lot of particle physicists, and they're just excited about being part of this collaboration, building such a big device. And as Dr. Wells said, it's a lot about engineering, and there's a lot of technology output and so on. To which I would generally say, yes, but if that's what you wanted, you could more directly invest into that. So when it comes to those big questions, I just don't think that this bigger collider is going to help us all that much. And as you already noticed, there have been a lot of promises since promises are saying too much, a lot of big statements since the 1980s about what those bigger colliders would find, starting with Tevatron in the United States, and then with LEP, the previous collider at CERN that we already heard about, and now with the Large Hadron Collider. It was supposed to find more than just the Higgs boson, and it didn't. And I think that's because of some problems with the predictions that physicists made, but this is a longer story. So I think my point is just that...
Oh, sorry to interrupt. Would you be so bold as to say actually using colliders is not actually going to answer the questions that they're seeking to answer? Or, I don't want to put words in your mouth, I'm just trying to understand the nature of your concerns.
I think it's not going to answer the questions that you heard about in this meeting. If you talk to particle physicists, they have much more specific questions that they want to answer, like they want to measure more precisely the mass of this particle or the interaction with some other particles. And those are questions that this bigger collider is basically guaranteed to give an answer to, but they're not very interesting questions.
So what would you have us do instead to examine some of those more fundamental questions of what's dark energy, what's dark matter, why have we got the matter-antimatter imbalance? How would you attack the problem? To find out more about dark matter, you do some astrophysics experiment, the stuff that's already on the way, basically, with a satellite mission and so on. And then there are more high-precision experiments that you can do, and also, again, those are already on the way, like with direct detection experiments and so on. When it comes more general to the question what we should do in the foundations of physics, personally, I think there isn't enough investment into studying the foundations of quantum physics with all that new technology, which is already being heavily invested in. So there's a lot of money and a lot of smart people, also in the UK, going into quantum technologies, quantum computing, quantum information, quantum optics, all this kind of stuff. But there's very little fundamental research. And that's just an obvious thing to do where a lot of progress could come out. Understood. Thank you very much, Chair.
Thank you very much indeed. Can I thank both witnesses for your evidence today? It's been a necessarily brief session, but I think we've got very clearly the essence of your case, and we're very grateful to have you both, in particular to have Sir David back in front of this committee. Thank you so much. I'm going to introduce our final panel. It's a panel of one, and it is someone, again, familiar to the committee, Professor Mark Thomson, who is the Executive Chair of the Science and Technology Facilities Council, the council within UKRI that principally funds the UK's contribution to CERN. And Professor Thomson is, very relevantly, a Professor of Experimental Particle Physics at the University of Cambridge and has previously been employed at CERN, where he played a leading role in the study of the W and Z bosons. Thank you very much indeed, Professor Thomson. You've been kind enough to sit through the evidence this morning. You've heard the to and fro, and there have been concerns expressed about the value for money that the UK is getting from its subscription in two particular respects, among others. One is procurement, and the other is the employment of UK scientists there. Give us your reaction to what you've heard this morning.
No, I share those concerns, and when I took over this job 6 years ago, one of the things I looked at was how were we really extracting the value for our investment in all of our international subscriptions, not just CERN. And I think the answer was scientifically absolutely yes. We get a fantastic value out of it. But in terms of that industrial return and perhaps the training opportunities for our early career scientists, we weren't getting as much as we could do. So we have started to put in place measures to actually really increase the return on investment in that sense, and that was part of the motivation for putting together our strategy, UK strategy for engagement with CERN, which was a joint STFC BASE/DCIT endeavour. And it really was to start to address those issues. And as you heard from Chris Hartley earlier, we are beginning to see positive evidence we are actually changing things in the right direction. It's putting real focus on trying to get better value out of the subscription. So I think it's a very valid question. I think the concerns expressed by the members of this committee are absolutely the right concerns. But with the right measures, we can actually turn that around. And that's really what we're trying to put a lot of focus on at the moment.
Thank you very much indeed. I'm going to turn to my colleagues, starting with Catherine Fletcher and then James Davis.
Thank you, Chair. Very good to see you again, Professor. How do you think we got ourselves into this position? You know, how did we end up with a mismatch of the UK's commitment and joy to fundamental physics and then, a huge differential compared to some of the other states in terms of what we were receiving directly?
Was not wanting to criticise our previous approach. I don't think we put enough focus on that economic benefits of our subscriptions.
You kind of said, thanks, we've got the internet, that'll do.
Yeah, well, not quite, but I think we'll use industrial return as a good example. Previously, within my organisation, the international liaison sat within our research department, effectively. We have now moved that into our business and innovation department, and these are the people who work with business all of the time. And strengthening the approach is strengthening the benefits. And I would also say our way of working with CERN, raising these issues with CERN and working collaboratively with CERN to solve them, again, is part of the solution. And we have seen a big shift over the last few years. We've still got a way to go. In terms of the personnel return, the human return, that is still work in progress. And CERN has changed the way its early career schemes are structured. And I think that's going to be very beneficial for the UK. And we need to keep pressing on actually looking at what measures we can put in the implementation of our strategy to actually change the dial basically on those measures as well. So it is doable, but it does require focus. And I think that's what I think our approach really is looking not just at the scientific benefits, but those wider benefits, and actually realising, well, we all know they're really, really important, but putting increased focus not just on the science, but on all of those other benefits.
Yeah, that's true. So, quite famously, the LHC is heading for an upgrade. It's only been through a very small percentage of all the different collisions it can do, and we're going to speed that up. How far down that process would you go in terms of evidence of scientific discovery off the back of the investment in the LHC before you committed to the FCC?
And that's actually a very good question. I think what we're doing at the moment through CERN is we're not making a commitment to the FCC, but what we're doing is we're putting in place all of the work, the feasibility, the design work that is necessary if we actually want to start that project in the 2040s. So we are now doing the work to enable work to start in the 2040s.
Do you know what the cost of the budget is? You know, because it's coming out of the current budget. Are we talking 10, 20 million quid a year?
I don't know. We could give you the actual number by written return. It's a small fraction of the CERN budget.
Yeah, I'm sure.
I can't remember the exact number.
Yes, forgive me, I interrupted you. Go
on. Yes. So what we're doing at the moment is actually doing the design work to make this an option for the future. And for that to be realised, we're going to have to do two things. Firstly, make the scientific case. I personally believe there's a very strong scientific case for the FCC, but we're going to have to convince others of that. And within the UK, as with all other major investments, we will have to make a business case, the economic case to the UK for why we're investing this through the normal Green Book procedure.
I think those both things, but I genuinely think I completely agree with both of those sentences, but do we make that decision tomorrow, or do we let the LHC run through, say, 50% of its collision data set before we make that decision, which is, 5-10 years?
That would be about, probably 5 years, 10 years time. I think that's an open question. I mean, I think genuinely an open question. We've not got to the point where we're making a decision point. The next stage is, I think it was referred to by Dr. Wells, there is this European strategy for particle physics, so there is a Europe-wide agreed approach for what the priorities are. That will be updated in the next few years, and that will lay out the pathway, potentially, to the future circular collider, if that's the route forward, and the timescales. I think one of the challenges that there are concerns about is leaving a big gap between the LHC and the next project, because all that happens then is you start to lose the capability, and it's not necessarily the scientific capability we're concerned about, it's the engineering capability. Once you've lost that expertise in high field magnets, for example, it's very, very hard to build that up again. So there are lots of dimensions to your question. I think it's an excellent question.
I think by 2041, 2044, the capability loss is not going to be high field magnets. It's the way the field's moving. It is an unknown that we will lose, but we don't know what it is yet. It's interesting. I'm very conscious of time, but thank you, Chair. But
thank you very much indeed,
if we have time.
Captain James Davis.
Thank you, Chair. If we take a step back and just ask the general question, why the UK should be committed to CERN?
I mean, CERN, in terms of, again, this is my personal view, and I'll come back to the more economic view. CERN is one of the pinnacles of particle, well, not just particle physics, but physics research. It is a beautiful paradigm of international collaboration to answer the most difficult questions out there. All major economies around the globe are investing in this type of research because they see, I think because they see not just the cultural and scientific value, and Dr. Wells made those points, but actually by investing in facilities like the facilities at CERN, you are trying to answer the most difficult questions out there. To do that, you have to invent new technologies. You can't just apply existing technologies to answer new questions. And by developing those new technologies, my view is you drive other areas of science. So the one example, I think I mentioned actually when you visited, was when we were designing some of the detectors for the LHC, some of the silicon sensors for the LHC detectors, we had to make them very, very radiation hard. Our team at the Rutherford Appleton Laboratory that did that then worked with Richard Henderson at the LMB, the Laboratory for Molecular Biology in Cambridge, in developing the technique of cryo-electron microscopy, which again needed radiation-hard sensors. He won the Nobel Prize for that. So this technique of cryo-EM is changing structural biology. So by driving technology to do the hard physics, you actually have impacts on other areas of science. So I think that's why we need to be in it. If we're not in this, we start to lose that technological edge.
Okay. Is Britain submitting a candidate for the next CERN Director General?
I think that's a question you would have to ask to the Foreign Office and DSIT colleagues.
Okay, fair enough. Do you think that the Foreign Office, DCIT colleagues and STFC are liaising with CERN member states over that possibility to a sufficient degree?
That would be through the Foreign Office, I think.
Okay, right, we won't pursue that any further. You've told us that you are committed to the idea of a future circular collider. Why should the UK government be committed to it? What are the reasons?
What I would say is I'm committed that we're doing the right feasibility study. I also believe the science case is correct, and I also believe it's the best machine to do that science. Mm-hmm. Now, until we actually have a full understanding of the cost and can make that economic argument, that's the point we'll have to take a decision. And I think one thing that has not come out, perhaps in some of the evidence previously in this committee, is we're not going to be asking for additional money on top, a significant amount of additional money on top of the CERN subscription. The costs of the future circular collider will largely come out of the CERN subscription, plus hopefully additional contributions from non-member states, so the US being one possibility if they choose to do so, and possibly additional contributions from the host states, again, if they choose to do that. So that's really where we are. This is not asking for a large amount of additional money on top of the budget.
Okay, right. So are you concerned that the funding for this project could divert funds from other infrastructure projects? No is the answer to that.
Because I think because that it is part of our ongoing commitment to CERN, as long as that remains, and I strongly believe it should do, it's not really asking for a large additional amount of money. Okay. So I'm not too concerned about that. And obviously within Science and Technology Facilities Council, we invest in lots of large research infrastructures, CERN being one of them, the biggest. Square kilometre array was mentioned previously. We look at that portfolio and try and balance the science and balance our investments to get the best science out and the best technological return out as well. So we're always balancing infrastructure investments. And we do that now across UK research and innovation for our kind of long-term infrastructure portfolio.
Thank you very much indeed. Just in terms of the next Director General of CERN, you said this is a matter for the Foreign Office. We are the second largest contributor to CERN. We don't have the current Director General. We're noted for the calibre of our scientists. Surely we ought to have a candidate, and why is it a matter for the Foreign Office rather than something that is an open part? You said transparency is the hallmark of CERN. Surely we should be doing this in public.
No, I agree. And in the previous Director General campaigns for CERN, there have been UK names in the mix, and I would hope that would happen in the current campaign. So yeah.
Right. Graham String and then Catherine Fletcher have some supplementaries.
Just a quick follow-up to that question, Richard, and then I've got another one. I mean, maybe I should know the answer to this, but why does the Foreign Office nominate and not the science?
I didn't say the Foreign Office nominated, but in terms of potential engagement with other countries at the diplomatic level, that would sit with the Foreign Office.
And so what is the process? If somebody is to be nominated, one of our distinguished scientists is to be nominated, do they apply or are they approached? What's the process?
There are multiple routes. There will be an open recruitment campaign which will launch sometime in April, I believe. Countries are also able to nominate. Individuals are able to self-nominate, and then there's a rather complex process through the Scientific Policy Committee of CERN, and also a little bit like a search committee that then narrows down the field. Then it goes to CERN Council, and CERN Council is the council of the member states of CERN, and that's where the kind of international dimension comes in, and that is often a ministerial or a foreign ministry decision. So it's an international governmental organisation.
You heard the arguments of David King and Dr. Hosenfeider. From what you've said, you don't agree with them. Can you approach the points that those two academics made.
No, I respect the. Of course, I respect the opinions. Particle physics and astronomy, so big science, our big investments, are a significant part of our physics research programme, just looking at physics on the whole. And if you look at the amount of money that the UK spends on physics compared to the rest of the portfolio, and I'd have to actually give you a number if you wanted that offline, this is not the largest fraction of UKRI's research investments. And I think if you spoke to the Institute of Physics, they would make the case that actually physics needs a larger investment because of the economic benefits. So I think in terms of that portfolio, that research portfolio, we're not out of balance. I think the opportunity costs in terms of people, which was an interesting point, I would actually argue it the other way. Because I think what initiatives like big projects like CERN or astronomy do, they attract more people into the field. And that's one of the things Science and Technology Facility Councils, we're very, very keen to promote this big science, this exciting science, but actually to reach out to diverse audiences, less privileged audiences, diversity in that sense, to try and encourage more people to go into science. And most of the people who go into particle physics don't stay there. They will go out into other fields of science, they'll go out into industry, they'll pick up skills in artificial intelligence. So I think there is a valid argument to make, and we would be able to make that actually by making these investments, you're actually increasing the pool of talent. So I think there are nuanced arguments in all of these areas.
We're doing a parallel inquiry into astronomy at the moment, and one of the facts that has come up in that is since PPARC was abolished, that physics and astronomy lost out, and the change in the funding councils meant there was less cash there. One, do you think that's true, and do you also think it's an argument that could be used for these to support these substantial amounts of money?
Yes. So I think the challenge. I don't think the transition from PPARC to STFC was the issue. I think the issue that people have seen is effectively long-term flat cash budgets and then increased cost of doing research that pushes down capacity. Now, what we've done, in fact, over the last, as part of actually this initiative to get the most value out of our big research investments, we have prioritised investments in early career researchers. So we've actually turned that around in some sense. So we're now investing more money in supporting the exploitation of these big facilities, and that basically means supporting more early career researchers. And that was an active decision to prioritise increasing the number of researchers benefiting from these facilities. That did not happen in the 2010s, but we are now turning that around, and that was an active decision to prioritise people, and that is having an impact actually. So I think it wasn't the transition of the research councils; it was more of a funding issue.
Right. A final question, if I may. I asked earlier panellists, maybe a question that's impossible to answer, how you choose between different areas of fundamental research, but it's a decision that has to be made, whether there is a straightforward answer to it. One of the recommendations of the NERS report from 9 years ago was to put the funding councils together so that those decisions could be made. Do you think that has worked, and are those really rather difficult questions, are they being approached now?
I would say we're part of the way there. I think there have been real success stories from the creation of UK research and innovation, and to come back to the topic today, I think one of the big areas, and actually it touches on the previous session, is our community within STFC. We have worked much more closely with the quantum communities in EPSRC, the Engineering and Physical Sciences Research Council, looking at how we start to use quantum technologies to actually address some of these fundamental questions about the universe. That was funded through a UKRI initiative. It was so we came together, made the science case, and we're now working, as I say, on driving technology, but to do fundamental science, And by doing that, we're driving the quantum technologies as well. So I think that's just one example of where something was at the boundaries between two different research domains that now has been enabled by the formation of UKRI. Has everything worked perfectly? We're still only 6 years into UKRI, so but I think the direction is very positive.
Thank you. Thank you very much. And finally, Catherine Fletcher.
Thank you, Chair. I want to pick up. So what we're trying to examine here is, are we getting value for money? Are we approaching the fundamental questions in the right way? And you've said in your previous comments that you're absolutely convinced that the science case is correct for the FCC. Could you just put on record why?
Yep.
And if this needs to slip into techie, then cool. But we're trying to translate, but I'm always slightly frightened of word soup.
Yep.
Counterpoints to realism of the underlying metaphor.
No, okay, I'll try and do that. So I think, firstly, in terms of this is not my opinion. This is the opinion of the wider particle physics community that the next machine, so the next frontier, should be a machine that focuses on just really looking at the Higgs boson. And the reason for that is the Higgs boson is nothing like any of the other particles. It is completely different. It's the reason we're all here, the reason why we have mass. Otherwise, we'd all be flying across the universe. That would not be very pleasant. All of our particles would just have to be massless. The Higgs boson determines the size of atoms because it determines the mass of electrons. So it's absolutely fundamental. It's there everywhere in the vacuum. So it's a really, really odd object. It's unique. It's the only particle we've ever seen that has no spin. We don't really understand its properties. The interesting thing about the Higgs is it gives mass to everything else. So if there's anything else out there that we don't know about, we expect the Higgs to connect to it. And that's really the driving argument around let's study this really odd object and see if it actually looks like what we think it does.
It's a cracking answer. Sorry, go on.
But then it's also, the idea is, because it might connect to anything else that's out there, it is the window that we might discover the stuff we don't know. And this is discovery science, so you're never guaranteed. That's phase one of the FCC.
So can I just come in on that? So we've discovered the Higgs. Am I wrong? It's 126 GeV, is that right? Yeah. And so we've discovered that with the LHC. If we can see it with the LHC, why do we need a bigger one?
There are a lot of measurements you can do with the LHC, but actually to do some of the other measurements, to really measure its properties precisely so we can understand, is the Higgs boson decaying into things that we can't see, which it could well be, invisible particles, which is possible. You can't see that at the LHC. You can measure that at the Higgs factory, and you can measure all of the couplings very, very precisely. So there are very strong scientific arguments for using that Higgs boson to discover the kind of uncharted world of particle physics out there.
Final one from me, Chair, if that's okay. So what is the one experimental data output that you would think would seal the case for the FCC? Is it a very clear energy loss in a box marked, we don't know what's here, from one of the collisions? What is it?
I think for me, and this is a personal opinion, I think it's measuring those couplings, measuring how strongly the Higgs interacts with all the other particles. Does that align with the predictions we see at the moment? But more importantly, there's a measurement you can make that you can measure how often the Higgs is decaying into things you don't see. You don't see them.
The LHC.
But no, with the future circular collider.
No, sorry. So this is what I'm getting at, is what piece of information that's currently accessible to us experimentally or potentially will create the case for the FCC?
That is an excellent question. We know we can make some of the measurements of the properties of the Higgs boson at the LHC. These really more subtle ones, we cannot do that. And that's really why and I'd say it's the global science community, certainly the European community, believes that a Higgs factory to study these properties in immense detail is the right next machine for...
I hear very clever people say this is absolutely what we need, but it's a big money and sum on trust. So is there any absence of data that gives us the indicator that these people are right?
Well, I think, as I say, it's a question of the nature of the Higgs boson And the only way we're going to find out what the nature of the Higgs boson is, really in real detail, and use that as a window for discovery, is a machine like the Future Circular Collider. We can go so far at the LHC.
So with the 95% of the additional data, is it almost just not worth collecting it? Should we just shut it down and build the FCC? No, seriously.
No,
if there's no data that's going to come out that makes the case for the FCC, why do we not just say, well, the LHC is Betamax and let's build a VHS and just do it properly? Why wait till 2040?
I think there are two separate questions here. The physics case for the FCC is there because of the Higgs part. The physics case for the high Lumi LHC is that really is at the high energy discovery frontier. So we heard in the previous session about supersymmetry, for example, may or may not be there. We don't really know yet. We've taken about 7% of the LHC data. We haven't seen anything yet. And again, if you're exploring the unknown, really there are two ways of doing that. These precision measurements of the Higgs, or smashing stuff together hard and doing that for a long time and really digging into that data to see if there are, this is discovery science, so there's no guarantee. But we need to take that data to come to the conclusion that actually there is nothing there at the LHC.
Tell you, here's why I'm bothered, and I promise I'll stop. So you've got a theoretical prediction from Professor Higgs and others that says, if you look somewhere here, you will find this. And that was shipped around, and a lot of people put their hands in their pockets and said, great. We are now saying there seems to be a gap in the case for the next step, when a lot of it's disproving a negative. But I'm very conscious of time. I don't wonder whether that's something we can return to.
Professor, I'll just answer that briefly.
I'm not quite sure I've got the question.
What is it that is convincing people that we need higher energies to understand a thing that we have seen successfully at lower energies?
Okay, so the Future Circular Collider is not a higher energy machine. It's a more precise machine that collides, in its initial stages, electrons, which enable you to make the precision measurements that you can really understand in detail the properties of this very mysterious particle.
So you're effectively saying that because it's slightly older design, that the detectors at the LHC are like looking at it through a net curtain and you want to look it through a microscope?
We'll go with that.
Right. Okay, thanks very much.
Thank you.
Thank you. I think it's been a fascinating morning, and I hope it's evident that the committee shares everyone's interest and enthusiasm about the science, but as a committee of Parliament, questions have to be made about priorities and future priorities. Were the FCC to be built, I think the UK contribution would be something like £1.3 billion, which is a huge amount of money. We had a one-off session on fungi a few weeks ago, which is minutely funded by comparison, and yet research in fungi is responsible for the discovery of penicillin, for example, in the years past, that have probably saved 500 million lives as a result. So these are important questions, scientific questions, and in some respect ethical questions as well, as to what's the best deployment of taxpayers' money. So these are the reasons behind our questions. I guess just to kind of wrap up, are you confident that spending 1.3 billion, should we make the case for a future circular collider, compares well with such alternatives? And just on Graham's point, do we have the right forum to decide that? Is UKRI best placed to decide between that or research into genetics or these colliders?
I think in terms of the case, and I'll come back to the fact we'll have to make a Green Book business case for this investment, focusing on the economic benefits. But I would like to step back to the previous discussions. A lot of the techniques we use in other areas of science, so for example, if you're looking at X-ray diffraction, for example, or if you're looking at synchrotrons, which are the machines that we use to discover to study biological matter. If we look at neutron scattering, the machines we have, for example, at Harwell, again, look at material sciences, biological systems. The origin of all of these technologies was particle physics. So by driving the technology, we are actually providing the tools to understand biological systems. So I don't think you can really look at it just purely in isolation. You have to look at how the contribution contributes to other areas of science in the long term. And
the structure for deciding that, is UKRI adequate? It might be a step forward, but can it resolve these questions?
I think UKRI, I would argue, certainly over the last 4 years, in terms of our major infrastructure investments, has come together and actually made decisions looking across all domains, including arts and humanities, social sciences, biological sciences, and physical sciences, and prioritised infrastructure investments between the two. Not at the scale of this, but at the scale of a few £100 million. So actually, I think that has worked incredibly effectively within UKRI.
Good. Professor Thomson, I'm very grateful, as the committee is, for your evidence this morning, for all of our witnesses. That concludes this meeting of the committee. Order.
Chair.
The proceeding has ended. 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 The proceeding has ended.